sometimes indicating that the limit of a function fails to exist at a point doesn't provide us with enough information about the behavior of the function at the particular point. To see this, we now revisit the function g of x, which is equal to the absolute value of x minus 2 over x minus 2. If you don't remember what the function g of x looks like, you can go back to the previous video to see how this function behaves in the vicinity of x is equal to 2. As we pick values of x close to 2, g of x does not approach a single value, so the limit as x approaches 2 does not exist. We say that the limit of g of x when x goes to 2 does not exist. DNE stands for does not exist. However, the statement alone does not give us a complete picture of the behavior of the function around the value of x is equal to 2. To provide a more accurate description, we introduce the idea of a one-sided limit. So we say for all the values to the left of 2 or less than 2 or the negative side of 2, we find that the limit g of x approaches negative 1. That is, when x approaches 2 from below, the limit of g of x is equal to negative 1. Thus, as x approaches 2 from the left, g of x approaches negative 1. Mathematically, we say that the limit as x approaches 2 from the left or from below is negative 1. Symbolically, we express this idea as the limit of g of x when x goes to 2 negative equals to negative 1. Notice how we have the negative sign here on top of 2 to indicate that this limit is actually a left-sided limit. So all of the x's we're testing are values of x that are less than 2. Similarly, as x approaches 2 from the right or from above or from the positive side, g of x approaches 1. And symbolically, we express this idea as the limit of g of x as x goes to 2 positive is equal to 1, indicating that we're only talking about the values of x that are greater than 2 when we express this limit or when we find this limit. We can now present an informal definition of one-sided limits. We define two types of one-sided limits. Limit from the left, let's say we have the function f of x, and it's a function defined of all of the values in the open interval of the form AC, and let L be a real number. If the values of the function f of x approach the real number L, as the values of x, where x is less than a, approach the number a, then we say that L is the limit of the function f of x as x approaches a from the left or from below. Symbolically, we say the limit of the function f of x as x goes to a from the left or approaches a from below is equal to L. Similarly, we can define the limit from the right. So if we have a function that is defined on all of the values on an open interval AC and L is a real number, if the values of the function f of x approach the real number L as x approaches a for all of the x's that are greater than a, then we say that L is the limit of the function f of x as x approaches a from the right or from above. Symbolically, we say limit of f of x as x goes to a from above or approaches a from above is equal to L. Now let's evaluate some one-sided limits. Usually the one-sided limit idea comes when we have piecewise functions. So let's say we have this piecewise function which is defined as f of x is equal to x plus 1 if x is less than 2 for all of the x's that are less than 2, and it is equal to x squared minus 4 if x is greater than or equal to 2. We want to evaluate the following limits. The limit of f of x as x approaches 2 from below, and the limit of f of x as x approaches 2 from above. Let's see how we're going to do that. Now let's note something. We have two branches for this function. So when we try to find the limit when x approaches 2 from below, we're interested in the values of x that are less than 2. So we're looking at the first branch of the function, since the first branch is defined on all of the values of x that are less than 2. If we want to find the limit from above, we're interested in finding what the function f of x approaches as x approaches 2 from above. So we're looking at all of the x's that are greater than 2. So we're looking at the second branch of the function since it's defined on all of the values that are greater than or equal to 2. So to do that, I created a table. This table, I'm going to choose numbers that are less than 2. And since I am choosing numbers that are less than 2, remember, the branch that matches that is f of x is equal to x plus 1. So I have chosen numbers here that are very, very close to number 2. I started with 1.9 and then 1.99, 1.999, and etc. Now, the second row, I found the values of the function f of x, which is in this case x plus 1. So the values were 2.9, 2.99, 2.999, and etc. Then you're going to round these numbers to the closest whole number you have. If you round them, all of them are going to match, and you will get the value 3. This will indicate that a limit might exist. To compute that limit, we're going to round all of these values to 2 decimal places. So if you do that, you're going to get 2.9. If you round this to 2 decimal places, 299. If you round this to 2 decimal places, you're going to get 3. If you round this to 2 decimal places, you're going to get 3. If you round this to 2 decimal places, you're going to get 3. So we have 3 values that agree. This indicates that the limit of the function f of x as x approaches 2 from below is equal to 3. So that is the first limit that I have. Next, we're going to build a table based on the values that are greater than 2. So I have chosen numbers that are slightly greater than 2. I began with 2.00001, 2.0001, 2.001, and etc. Then I found the value of f of x at each of these points. So you will end up with 0.0004, 0.004, 0.004, and etc. If you round these numbers, if you round these original numbers to the closest whole integer, you're going to end up with 0. This suggests that a limit might exist. To find the limit, we're going to round these numbers to 2 decimal places. So if you round this number to 2 decimal places, you're going to get 0.41. If you round the second number to 2 decimals, you get 0.04. If you round this to 2 decimals, you're going to get 0, and here 0, and here 0. Remember, we're rounding these numbers to 2 decimal places to figure out the limit. So in this case, we can indicate, since we have an agreement here, we can say that the limit of the function f of x as x approaches 2 from above, notice here we're working on all of the x's that are greater than 2, is equal to 0. Notice how the limit from below does not agree with the limit from above. And that is going to tell us that the limit from both sides does not exist. So the limit from below exists and it's 3. The limit from above exists and it's equal to 0. But those limits do not agree. So that tells me that the limit from both sides does not exist. Let's take a look at another example of a function. Let's try to find the limit. Let's find the one-sided limits graphically. Let's say this is the graph of the function f of x. Let's say this is just the graph of the function f of x. The function f of x is a piecewise function. We don't have a formula for f of x, but still, because we have the graph, we can see or we can estimate the limit of the function f of x or the one-sided limit of f of x. So let's say we want to find the limit of f of x when x approaches 2 from below. So here is the value 2. We want to approach 2 from below, so we're looking at this side. We're coming from that side. Coming from that side will tell us to follow this graph, this piece of function, which is in this case going to stop here, indicating when x approaches 2 from below, the function is going to approach the number 3. And that's why the limit of f of x when x approaches 2 from below is equal to 3. Similarly, if I want to find the limit of f of x when x approaches 2 from above, then I'm looking at all of the x's that are greater than 2, and I'm coming from this side. I'm approaching 2 from above. As I approach 2 from above, I know that I have to follow this piece of graph of function. So I see here that when x approaches 2, the function is approaching y is equal to 0, which is this value, which is the x-axis. So that's why the limit of f of x when x approaches 2 from above is equal to 0. Therefore, the two-sided limits of the function does not exist because the limit from below does not agree with the limit from above. They do not approach the same value. And you can see it clearly from the graph of the function. Now we have to connect the one-sided limits and two-sided limits. Remember, we said the one-sided limit is the limit of f of x when x approaches either from above or below. So this is when it approaches from below. This is when it approaches from above. If these both exist and they agree, then we can find the limit of the function f of x when x approaches 2 without looking at whether we're going to approach this from below or above, because we have done that already here. If these exist and agree, then the limit, the two-sided limit, should exist as well. Let's look at the theorem. If we have a function f of x and it's defined on all of the values in an open interval containing a, with the possible exception of a itself, remember, the value of the function at a is irrelevant to the limit. And let L be a real number. Then the limit of f of x is equal to L as x approaches a, if and only if the limit from below, the limit of the function f of x as x approaches a from below, is L, and the limit of f of x as x approaches a from above is L. Meaning, if the limit from above and the limit from below exist and they agree, then the two-sided limit is going to exist and it's equal to the same number. Infinite limits. So, infinite limits from the left. Here's the theorem. Let f of x be a function defined on all of the values in an open interval of the form a, b. Then, if the value of f of x increases without a bound as the values of x, where x is less than a, approach the number a, then we say that the limit as x approaches a from the left is positive infinity, and we write it. The limit of f of x as x approaches a from the left or from below is equal to positive infinity. If the values of decrease without bound as the values of x, where x less than a approaches the number a, then we say that the limit as x approaches a from the left is negative infinity, and we write it. The limit of f of x as x approaches a from below is equal to negative infinity. Infinite limits from the right. So if we have the function f of x and it's defined on all of the values in the open interval AC, if the values of f of x increase without a bound as the values of x, where x is greater than a, approach the number a, then we say that the limit as x approaches a from the left is positive infinity, and we write it in this format. If the values of f of x decrease without a bound as the values of x, where x is greater than a, approach the number a, then we say that the limit as x approaches a from the left is negative infinity, and we write it in this format. Two-sided infinite limits. So if we have the function f of x defined for all of the x's that are not equal to a in an open interval containing a, if the values of f of x increase without bound as the values of x, where x is not equal to a, approach the number a, then we say that the limit as x approaches a is positive infinity, and we write the limit of f of x as x approaches a is equal to positive infinity. If the values of f of x increase without bound as the values of x, where x is not equal to a, approach the number a, then we say that the limit as x approaches a is negative infinity, and we write it like that. Note that this doesn't mean a limit exists. It just reflects the behavior of the function at a particular point. And this is clear when you graph functions, and you can refer to the previous video to see an example of something like that. Let's look at the first function. H of x is equal to 1 over x minus 2 all to the second power. So as I mentioned, the graphical approach is probably the clearest approach when it comes to determining limits of this format. And then I'm going to give you a theorem that you can base your information on in order to find these kinds of limits. So this is the graph of the function, and we want to find the limit of h of x as x approaches 2. So we're going to approach 2 from above, and we're going to approach 2 from below. Notice how if we approach 2 from above, then the graph of the function is increasing without a bound. So we're going to write it. The limit of h of x as x approaches 2 from above is equal to positive infinity, because the function is increasing without bound. Let's approach x is equal to 2 from below. You notice when we approach x is equal to 2 from below, the function increases without a bound again. So we write down that the limit of h of x as x approaches 2 from below is equal to positive infinity. This will conclude that the limit, the two-sided limits of h of x as x approaches 2 is equal to positive infinity. Let's look at the next function. G of x is equal to 1 over x minus 1. If you graph it, you're going to get this function. Now we want to find the limit of g of x as x approaches 1. So first we're going to approach it from below and from above. So here is number 1. If we approach 1 from above, then the function increases without bound. This will indicate that limit of g of x as x approaches 1 from above is equal to positive infinity. When we approach x is equal to 1 from below, notice how the graph of the function is going to decrease without bound. We can write it as the limit of g of x, there is a typo here, sorry, g of x when x approaches 1 from below is equal to negative infinity. This concludes that the two-sided limit does not exist. That's because the limit from above does not agree with the limit from below. Although both of them give us a good indication of what happens to the function, we cannot determine the behavior of the function around x is equal to 1 because the limit from above does not agree with the limit from below. In the previous example, we indicated that the function increases without a bound when x approaches 2 because the limit from below agreed with the limit from above. But we can't say that in this case. Let's look at this theorem which is going to save you some time. So I want you to pay a very good attention to this theorem. It's very important. If you have n, it's a number and it's a positive even integer, then the limit of 1 over x minus a all to the n power as x approaches a is equal to positive infinity. What happens if n is a positive odd number or a positive odd integer? If n is a positive odd integer, then the limit as the limit of 1 over x minus a to the n power as x approaches a from above is positive infinity. The limit of 1 over x minus a to the n power as x approaches a from below is negative infinity. Let's apply this theorem. Let's find the limit of 1 over x plus 3 to the 4th power as x approaches negative 3. First of all, we need to find n and determine whether n is positive odd integer or positive even integer. So n here in this case is equal to 4. and this is positive, and it's even. So we're going to use the first branch of the theorem, which says if that is the case, then the limit of 1 over x minus a to the n power as x approaches a is equal to positive infinity. Now we found n. This part, if you notice, does not agree with that part, so we need to deconstruct this part to match that one. To do that, I'm going to rewrite it. I'm going to say this is equal to the limit of 1 over x. Remember, plus can be written as minus minus. So here is the minus for the formula, and here is the minus for the number. So minus negative 3 all to the 4th power when x approaches negative 3 from above. Okay, so this number matched, and the sign matched our formula. We can say confidently that this is going to be equal to positive infinity. Because the two-sided limit is equal to positive infinity, it's easy to say that the one-sided limit is going to be positive infinity as well. Because if the two-sided limits exist, that means the one-sided limit exists and agree. Let's look at the second example. The second example is exactly the same, but here we're looking for the one-sided limit, which is we're looking for the limit when x approaches negative 3 from below. Using the same idea here, and because this exists, I know that the limit from below is similar, which is equal to positive infinity. Let's look at the next one. So I know from the theorem that the two-sided limit exists, and based on that I found the first one and the second one. So I'm going to say this is equal to positive infinity based on this part. Now let's look at this example. Notice how the difference here is in n. N in this case is positive, but it is odd. So in this case, we have to test for two-sided limits, and then if the two-sided limits give us the behavior of the function and both of these behaviors agree, then we can say that the two-sided limits will give us the same behavior of the function. So n is equal to 3 and it's odd. So we're going to follow the second theorem. The second theorem says the limit, if n is odd, then the limit of 1 over x minus a to the n power as x approaches a from below is negative infinity. And the limit of 1 over x minus a to the n power as x approaches a from above is positive infinity. So we said again n is odd in this case. So we're going to apply this theorem. Now, we have a is equal to 2 here, so it matches. So we have a is equal to 2 and it matches. So we can apply it right away. So the limit when x approaches a from above is going to match this part. And the answer for this part is going to be positive infinity. So the behavior of the function, it increases without a bound when x approaches 2 from above. When x approaches 2 from below, that matches this part of the theorem. So we're going to say the behavior of the function decreases without a bound when x approaches 2 from below. Since that is the case, I can tell that the limit, the two-sided limits, actually does not exist. I can't tell the behavior of the function at the point 2 because when I approach it from above, the function increases without a bound. When I approach it from below, the function decreases without a bound. I hope this gave you an idea on how to figure out the one-sided limits numerically and from graphs. Next, we're going to talk about the limit laws, which is going to help us compute limits algebraically. Thank you for watching, and I will see you in a different video.